We'll first talk about searching in B-trees, and then we'll talk about insertion. Let's suppose we have the tree given here, and I want to search for R. I start at the root, as you would expect, and I see that R is greater than M, and so I'm going to go down, let me change colors, down this branch here. Then I look at the first key. Is R less than Q? No. I look at the next key. Is R less than T? Yes. So I'm going to go down this second branch, and then I can search through the keys in that node and find R. Here's the actual algorithm. So we are first going to look through the keys and find the index of the key. Let's see, the key that is greater than or equal to K, the key that we're searching for. Then we are going to, if the key is equal to that, we're simply going to return the node. So this is the node, and this is the key. So found, and we return it. Otherwise, if we're a leaf, then it's not found. Otherwise, we're going to make the recursive call. We're going to call it with the appropriate child that we found by looking for the index I. So that was this part here. We look at Q, we looked at T, and we found, oh, the T is greater than R, so we're going to go down that. So I would be equal to 1 in that case. So that's what this child is. We pass in the key itself and we do a search. Now notice there's one extra thing, and that is we need to read in the child from disk if it isn't already in memory. Since we're targeting applications where the tree is going to be stored on disk and we're only going to be able to have part of it in memory at a time, that's going to be important. So the question is, how many pages are we going to access in this tree search? So how many pages? And this is memory pages or disk pages. And so how many nodes are accessed in a search? Well, it's going to be the order of the height of the tree, and in the last video we showed that that is bounded by log base t of n, order log base t of n. Now, since the number of elements in a node is bounded by 2t. Now remember, in the last video we showed that xn, which is also known as k, is less than or equal to t minus 1, is greater than or equal to t minus 1, and is less than or equal to 2t minus 1. And so xn is less than 2t. And so since that is true, the while loop, which is right there, is going to be bounded by x sub n, which is order t. Okay, so if the number of pages is accessed is order log base t of n, then that's the number of recursive calls we're going to be making, because we're making a recursive call for each node or each page. And for each recursive call, we're iterating t times, which is constant across all recursive calls. So the total time is going to be order t log base t of n for the search. Okay, so now let's look at insertion. And let's just do one more example. We did an example in the last video, but let's do one more. Let's say t equals 2 again. So the number of keys is greater than or equal to 1, less than or equal to 3. So if we insert x, we get x, then f, we're going to get fx, then we'll insert m, fmx, then we'll insert b, and so we're going to pull m up, drop f and x down as children, and insert b into its proper place. Then if we do g, b, f, g, and then if we insert j now, it gets interesting. We come down here and we see that we need to split that node. So we take f, bring it up into its parent, b, g, b is there. G is going to go between f and m, and j is going to be g and, oh my goodness, g and j, right, like that, and then x. So what's the actual algorithm? Let's show it. Let me bring it up here. Let's see, page 494. Well, here's another example, another graphical example. You can see that we need to split this node, so we take S and we're going to promote it up into here. And then we take everything less than S, bring it into that child there, everything greater than S into that child there. All right, now on page 496. This is showing the same thing, except we're splitting the root, so we're creating a new root. And 494 again. There we go. There's the algorithm. Now let's see if we can walk through this and keeping a graphical example. So I'm going to have a tree. It looks something like this. And we're going to make changes to it. All right, so we create Z in the first step. And let's see, X is going to be here. And we have Y is the child we're going to split. So let's say this is Y. So we start by making Z a leaf if Y is a leaf. So and we need to draw Z here. Let's make Z this right here. So Z is now going to be a leaf if Y is a leaf. All right. And we set the number of children of Z to be t minus 1. Okay, t minus 1. Now remember, t is that parameter we set to be the size of the nodes. If Y, well, we're splitting Y. Therefore, we know that the number of elements in Y is equal to 2t minus 1. And so if we split Y we're going to end up with t minus 1 over here, t minus 1 over here, and then 1 that's going to be promoted. So that's why the new size of z is going to be t minus 1. And then we copy the keys from y to z. So now that's going to take all of these and put them up into z, all of those keys. And we're also going to copy the children from y to z. Now we update y's size to t minus 1. Now what we need to do is we need to update x. So let's change colors here. So here's x, and we did have some key here, ki, and then kj, and it was pointing to y. What we're going to do is now we're going to insert some new key, and we're going to have to update everything. So everything that comes after key k sub j is going to have to move one index over. And so that is lines 11 through 12 of the algorithm right here. So we're moving all those keys over. Now we're going to set the child here to z. So that's line 13. Then, let's change colors again. We're updating the keys. So that's similar lines. We were updating the children pointers before. Now we're going to update the keys. And then again, we need to update the key for y. Well, what this is doing is this is promoting y's middle key. So it's this right here is going to be promoted up into its parent. And that's line 16. Then we increment the number of children that x has, and the number of keys, and then we write all three. Now let's show one more figure. Now this is actually a lot simpler than it looks. This is inserting a key into a non-full node. So if we have a tree node, we're going to be able to insert a key here. So the first thing we're going to do is we're going to suppose this is where the key belongs. We need to take all of the keys after that and move them over. And that's what this is doing here. Then we insert the key itself and we write the disk. Now this is if it's a leaf. We're only inserting into leaves. Otherwise, we're going to read, split the child if necessary, and then make a recursive call to insert non-full. Now, there's an important subtlety here. And that's this splitting while we're going down to insert. If I have a tree, and I want to insert a key, say here. By inserting that key, if this node is full, then I'm going to split it. And what's going to happen is some key is going to get promoted up to its parent. Now, what if its parent is full? Well, that could be a problem because then we'd have to split it and it would cascade up and it would be very inefficient. So what we're going to do is while we're searching for where the key belongs, we're going to go down the tree, and any node that's full, we're going to split and promote one of the keys. By doing this, when we insert into a leaf, if we need to insert, it will not be full. We're guaranteed because we're going to split full nodes as we go.